Hello, Chem 30 students. So today we are looking at hydrocarbon derivatives. So kind of moving on to, different versions of these organic compounds that we're looking at with different types of functional groups. So we're going to be looking at the organic halides and the alcohols today. A few curricular outcomes to keep in mind. So just like the other ones, you have to be able to name and draw these compounds and just to be able to identify them based on their functional groups. The difference with the two types that we'll be looking at today are that there can be multiple occurrences of the functional group, okay, for halogens and alcohols, whereas in the previous types of compounds we looked at, and in some of the ones we'll look at coming up here, carboxylic acids and esters we'll be looking at in the next lesson, there can only be one instance of the functional group. So these ones are a little bit different. They're not actually that much more complicated though, because with halogens and alcohols, when you have a multiple group, it basically ends up being the same as if you have like two methyl groups, right? So, and we've already done that with some of like our alkanes and stuff. And hopefully you saw that those weren't too hard. You just have to remember to put in that prefix of like dimethyl, for example. And so we'll look at that with those types of compounds today. You also need to be able to identify the types of compounds based on like the halogen functional group is going to help. Like when you see a halogen attached to a hydrocarbon, you're going to know that you're dealing with an organic halide because of that halogen. And same thing with the hydroxyl linkage. This is for alcohol, so we'll look more in detail at that later. But basically, you do have to be able to identify that something is an alcohol because it has that hydroxyl group. Just looking at knowing some of the significant organic compounds, identifying and describing is kind of what we would already be looking at when we're looking at naming and drawing, but also just knowing a little bit about their applications. So we'll look more in detail at that today. So make sure that you do have some idea of the common uses of these compounds. Then also just being able to compare amongst all of the different types of organic compounds that we're looking at in this unit, you need to be able to compare boiling points and solubility. So usually you'll have to be able to rank them from like highest to lowest and things like that. So, yeah, this is the same thing as just talking about the fact that you will only have one of those. You could have more than one of those functional groups for halides and alcohols, so we already went over that. All right, I apologize for the messy notes. I started working on a recording and it was like first thing Monday morning and I just wasn't happy with how it was going, so I decided to come back and start over again. I was only a few pages in, but I felt like I was blabbing on too much, so hopefully I can cut that down in this recording. All right, so organic compounds in which one or more hydrogen atoms have been replaced with a halogen atom is the organic halides. So keep in mind that halogens are group 17 atoms. Okay, so group 17. Now, organic halides could be polar or nonpolar, or they could have like a relatively nonpolar end, which is always going to be the hydrocarbon end, and then a polar end, which is where the halogen is, okay? So if you remember back to Chem 20 when we talked a little bit about electronegativity, just keeping in mind if we look at our halogens here, this value here represents your electronegativity, and so remember fluorine is our strongest electronegativity. Everything in the periodic table trends in increasing electronegativity towards fluorine. So that means going from the bottom to the top and from the left to the right is how we see electronegativity increase. And if you look down this chart here, you can see we go 4, 3.2, 3.0 down to 2.7. And carbon is at 2.6. So there is a pretty big difference in electronegativity for these first three halogens and carbon. Iodine, not so much. So that's why we can see some of our organic halides having less of that polar quality, right? There's only a difference of 0.1 between these two. So you can see that trending here, right? So in this this is a map of electron distribution. So remember, high electronegativity means that an atom has an ability to pull electrons towards itself quite strongly. So fluorine is the most electronegative atom on the table. And so what we end up seeing here is that the electrons, you can see this red indicates a high electron density and blue indicates low, right? And then yellow and green are our intermediate colors. And so basically what we end up seeing is because fluorine can pull those electrons towards itself and we see that high density around it, remember that means we would represent this molecule as having a slightly negative end where the fluorine has pulled the electrons over more in that direction, and then a slightly positive end over here at the hydrocarbon end where the electrons from this part of the compound have been pulled away, leaving a slightly positive charge. So it's kind of like with ionic compounds where, we have a negative ion and a positive ion, except for instead of a complete transfer of electrons like we see in an ionic compound, here we just see a shift in the distribution, okay? But they're still being shared amongst all of the atoms. So this is where we start really getting into boiling points and solubility for the next few types of compounds we'll be looking at. With organic halides, we see that they have higher boiling points than similar hydrocarbons, so like the alkanes, alkenes, and alkynes. And the reason for that is because of this, now we all of a sudden have atoms bonded that have quite high electronegativities. So remember back to Chem 20 when we learned about intermolecular forces. There were three main ones, right? There was London dispersion, which is sometimes called London forces, sometimes called dispersion forces, so make sure you recognize both. And all types of molecules have this London dispersion force, okay? Then if we think about dipole-dipole, oh, and one other thing to be aware of is that London dispersion forces, the main component that affects the strength of the London dispersion forces is just the number of electrons, okay? So basically, if you have similar compounds that have like the same types of atoms, the one that has more atoms is always going to have more London dispersion forces, okay? So that would be true for like just straight alkanes, for example. If you compare like methane to octane, octane is going to have a higher boiling point because it has more atoms, more electrons, so its London dispersion forces are going to be stronger. Now, dipole-dipole forces, keep in mind, are present for all polar molecules. So here we do see with this CH3F, we see that there is polarity, right? We see a pretty big difference in the electron distribution, which means that this molecule exhibits dipole-dipole intermolecular forces. So that means if you were to compare like the similar hydrocarbon, so the similar hydrocarbon to this would be methane, CH4, right, where we have carbon with 4 hydrogens, and in this one we've had one of those hydrogens replaced with fluorine. So if we were to compare methane and CH3F, basically what we would find is this one has dipole-dipole forces, methane only had London dispersion. So that means there aren't as strong of forces keeping this methane bonded to another methane. Remember, intermolecular forces are not talking about the bonds between atoms in a molecule. They're talking about the bonds between different molecules that keep them together as like a liquid, for example, right? So that it's all one substance, right? So that it all stays together. So these bonds are going to be more easily broken because they're only the London dispersion, whereas with this molecule, we would have London dispersion and dipole-dipole forces, okay, because of its polarity. With the stronger forces, these types of molecules will be harder to break apart from each other. So that means you need to put more energy in order to separate them into like a gas, for example. So that's why we have a higher boiling point, is because you need to heat it up more, put more energy in order to give the molecules the amount of energy that they need to be able to break those bonds from each other and separate into a gas. Okay. Now the last type, which we'll look at more when we get into alcohols, is hydrogen bonding. So this is the strongest of the intermolecular forces, and this is only present when we have hydrogen directly bonded to either a fluorine, oxygen, or nitrogen, sometimes chlorine, but these are the main ones. So just keep in mind it has to be a direct bond. So with this one, we have hydrogen in the molecule and we have fluorine, but because they're not directly bonded to each other, we don't have hydrogen bonding. Okay, so just make sure you keep that in mind with that molecule there. So main takeaway here, just other than our little bit of a recap of the types of intermolecular forces that we really want to keep in our minds as we move forward, because on top of knowing how to rank the boiling points and solubility, you need to know why they are ranked that way. So that's why I wanted to recap those points from Chem 20. So the higher boiling points, right, wait, what was I going to say there? Higher boiling points. Yeah, basically just keeping in mind like that the organic halides are going to have higher boiling points than like alkanes and alkenes. Okay. Let's see. What about solubility? So with alkyl halides, they have low solubility compared to a lot of organic compounds, but they're still higher than similar hydrocarbons. So again, if we were to compare like the CH3F to methane, this would have a higher solubility because, again, of its polarity. And CH4 doesn't have that polarity. So remember, with polarity, you would have to have a fairly decent difference in the electronegativity of the atoms. And also you need to look at symmetry. So with the CH3F, we see that it's not symmetrical, right? Because we have this molecule kind of throwing off the symmetry. Whereas with CH4, you would have a symmetrical shape because you would have hydrogens all the way around that carbon. And so keep in mind the way that solubility works is like dissolves like. Okay, and so with water, we know that water is polar. And so the more polar that something is, the more likely it is to dissolve in water. Okay. So if we look at, here's a table that shows the solubilities of alkyl halides in water. And we want to look at this and think a little bit about the pattern, because this is a good thought process to kind of go through to think about why this would be true. So if we look at the top here, we see like very soluble, soluble, slightly soluble. So we can see that the solubility is decreasing as we go across. And what's changing as we go across? Well, we go fluorine, chlorine, bromine, iodine. And look at what happens here in the table. Fluorine is 4, chlorine is 3.2, bromine is 3, and iodine is 2.7 in their electronegativity. So here, where you're going to have quite a large difference between the electronegativity of fluorine and chlorine, our molecule will be quite polar, and so we see that it's very soluble. Whereas with the CH3 with an iodine attached instead of the fluorine, we only see slight solubility, and that's because there's not a large difference between the iodine and the carbon in terms of electronegativity. So decreasing solubility as we see that change in electronegativity. What about what's happening as we go down the table for each of these? We can see that for all of them, the solubility decreases as you go down. So we start with just one carbon with the fluorine attached, and it's very soluble. Then we have 2 carbons, it's soluble, 3, it's slightly, and 4, it's insoluble. And same thing here, right? Soluble, slightly, slightly in, slightly, slightly, slightly in, right? So it's always decreasing regardless of how that happens. And it's decreasing as the chains get longer. And the reason for that is because all of this hydrocarbon chain is not polar, right? The only really polar kind of difference we would see is at the very end here, where the fluorine will be pulling off of this carbon, but it's not enough to make it polar enough to dissolve. So this one is actually insoluble. So just keep in mind, as your non-polar component increases in size, the effect of this, the electronegativity of that halogen decreases. And so we see solubility decreasing. Okay, so keep that in mind with these different types of compounds. If you were asked to compare on a test, like you wouldn't be asked to choose between, let's see. You wouldn't ask to be choose between like this one and this one, like which one would be more or less, because this one has only 3 carbons and this one has 4 carbons, but there's a difference in fluorine and chlorine. That's a little bit complex. The most you would be asked to do would be to choose between 2 of the same that have a longer carbon chain, or 2 of the same that have different different halogens. So then you would have to know that even this, like you wouldn't have to know that both of them are insoluble, but you would have to be able to say like the one with fluorine is more likely to be soluble than the one with the chlorine. Okay, so those are the types of comparisons you'd be asked to do in test questions. Okay, the last thing to be aware of for the alkyl halides is that a lot of the ecologically damaging or toxic substances that we see are part of this organic compound group. So you might have heard of DDT, probably especially if you took Bio 20. Same thing with PCB. DDT is pretty commonly known because it was an insecticide that was used pretty widely all over the world for a long period of time, and it ended up having pretty devastating environmental effects. Killing off lots of animals that weren't intended to be killed off. Also, it got into, because it bioaccumulates, so it builds up in the tissues of organisms. So it went up the food chain, and as it goes up the food chain, it becomes more concentrated in the tissues. So it's more deadly to organisms that are higher up the food chain. And then the other problem with that is one of the big results that happened was that birds, because it accumulated in their tissues, it ended up affecting their reproductive capabilities. One of the big effects was that their eggs weren't able to form eggs with hard shells. So the egg shells became really, really thin, and basically when the parents would go to sit on the eggs, they would just be crushed. So there was a huge decline in bird populations. Ontario was a big place with that. The bald eagle population died off pretty badly, but they've rebounded since then because DDT has been banned and is only used in, like a few third world countries where that kind of regulation isn't really intact. One problem also with this is that it stays in the environment. It's called a persistent organic pollutant. So it stays in the environment for a long, long time. So it's taken a long time. Even after the banning of it, it's taken a long time for it to be removed from ecosystems. So it has long-lasting effects that are quite negative. So just being aware of that, use and kind of historical thing about alkyl halides. Okay, one type of isomerism that we didn't talk about when we looked at structural isomerism is cis and trans isomers. So with cis and trans isomers, basically what we're doing is identifying where functional groups are located with relationship to a double bond. So all you really need to know is cis is always on the same side and trans is always on the opposite side. So if we have basically 2 versions of this, like dichloroethene, right? Both of these are dichloroethene, but they're actually going to have different chemical properties depending on where those chlorines are located. So even if they're both, and actually I should have included that, they're both 1,2-dichloroethene, right? So if you want to indicate to whoever's reading about, this chemical compound you're writing about, if you want to indicate to them the actual structure, you need to tell them where those chlorines are located relative to each other and the double bond. So with cis, both chlorines are on the same side of the double bond, and so we can see that here pretty clearly. Whereas with trans, we have the double bond. One chlorine is coming off the top of one carbon and the other one is off the bottom. It shouldn't matter. In Chem 30, you don't have to, you wouldn't get marked wrong if you would have done the chlorines here and the hydrogens there, okay? And same thing here, as long as they're on the same side, it's okay if you would have done 2 chlorines up here and 2 hydrogens up there. Okay, so don't stress about which side they are on relative to the hydrogen, but just relative to each other and the double bond, okay? One thing to keep in mind moving forward though is that the cis and trans is not something in your curricular outcomes, so you technically don't need to know it. I haven't seen it in any of the questions, like the diploma questions that have ever come out. The only thing is, I did see a little bit of a question about it on page 444 in your textbook. Question 13 talks a little bit about trans fats. And that is, something that you've probably even heard of before in terms of diet and things like that. So it is an interesting thing to be aware of and how that applies to the chemistry, even within our food. So, but just be aware that it's not something you need to focus, really intently on for studying for tests. So let's talk about naming organic halides. So basically, we have the prefix, which gives the name and position of side groups, just like we've looked at up until now. So for alkanes, the halogen is given the lowest carbon number. And for alkenes and alkynes, just like before, the multiple bond is given the lowest number. So just make sure when you're numbering your molecule that if it's an alkane, the halogen gets numbered first, but otherwise your multiple bond does. The root, as always, indicates the number of carbons. We can have a cyclo a group on here, basically, so for an organic halide. So just remember, you'd put on the cyclo ahead of the root that indicates the number of carbons in the parent chain, if that's present. And then, just like before, you're going to end it with either ANE, ENE, or YNE for the alkanes, alkenes, and alkynes, or if you have benzene, it ends with benzene. In terms of your halogen side groups, there's only a few possibilities for the halogens. So there's bromo, chloro, iodo, or fluoro. So just be aware of how you modify those names from like bromine, chlorine, iodine, fluorine, right? So you're changing the endings to O. And then when you put it together, this was like a visual that I got off the internet, so it's kind of weird because they separate it. Keep in mind we don't space between there, so it would just be chloromethane or fluoroethane. Okay. So let's try an example of this. So we have this structure here. The first thing we want to do is number the carbons and name the root structure. So because in this structure we have a multiple bond, we want to number the carbons that contain the multiple bond the lowest. Over here we have a chlorine, so that's our halogen, and over here we have a methyl group. So we're going to make this our parent chain, and we want to start numbering at this end so that our double bond has the lowest value. So this will be our carbon 1, carbon 2, and this one will be our carbon 3. So number the carbons, name the root structure. Well, in our parent chain we have 3, so that's going to be prop. And then we have a double bond, so it's going to be propene. Okay, now we're going to have to insert the number of the bond there as well, but we'll get to that in a minute. Then we want to name the branches. So on carbon 2, we have a methyl group. And on carbon 3, we have a chlorine, which we call a chloro group, right? So when we name this, we want to go alphabetically. So we're going to start with chloro. So we're going to go 3 chloro. Oops, I'm getting kind of low there. 3 chloro. And then 2 methyl. Oops. Sorry guys, I forgot to do the dash in there, so don't forget the dash between any numbers and letters. 2 methyl. And then we have the propene with a double bond on carbon 1. Now, prop 1-ene. I have read that you could just call this 3-chloro-2-methylpropene. However, for us, we do want to make sure that we identify the location. The reason why I've heard that it's identified as like not having to have the 1 in it is because there's only one possible location for the double bond, but that doesn't totally make sense to me, because to me it could be on this carbon as well, and then you would name this one carbon 1. Maybe that's why they're saying it, because you would number it differently then. But yeah, to me I would say go on the safe side and just label it. Okay. All right, so that is organic halides. Hopefully that made sense because we're moving on to alcohols now. If you want, you can always pause the video right now and go in and try some of those practice problems that I listed at the end here. So those reading through a couple of examples that are on page 418, that'll give you a few more types of these organic halides to look at, and then you can try on page 418 number 1 to 5. But moving on to alcohols, alcohols are hydrocarbon derivatives that contain a hydroxide, right? So this is our polyatomic ion there, hydroxide. But when we're talking about it in this sense, we call it a hydroxyl functional group. They always have to keep things just a little bit complicated for us, right? So a hydroxyl functional group. Now, what is a hydrocarbon derivative? I've kind of mentioned it a little bit here. Hydrocarbon derivative is basically just any hydrocarbon that contains other atoms like oxygen, halogens. So this is where we're starting to move away from what we've looked at so far, which have been like alkanes, alkenes, alkynes, and cyclo versions of those, and aromatics. All of those so far that we've looked at have only contained carbon and hydrogen. So all of the ones that we'll look at moving forward have different types of atoms in them, and so they're called hydrocarbon derivatives. The hydroxyl group forms hydrogen bonds. So remember we talked about that in our organic halides, the different types of intermolecular forces. Remember, if you have hydrogen directly bonded to fluorine, oxygen, or nitrogen, you have hydrogen bonding. So with a hydroxyl group, we have hydrogen directly bonded to oxygen. So because we have that very strong type of intermolecular force, alcohols have high boiling points compared to their similar hydrocarbons. That would be like alkanes and alkenes, right? Okay, and then the last thing here is just that because we have that polar hydroxyl group, the short-chained alcohols are going to be very soluble, right? So we'll see that same kind of pattern that we saw with the organic halides, that as long as you don't have a really long chain that's kind of non-polar on the one end, we're going to see that high solubility. All right, over here, a little bit of information about some of the chemistry of rum. Obviously, alcohol is an important component to that. And then there's also some other components that we'll be looking at later on, like esters that give it like fruity aroma and things like that, and other flavor compounds, as well as the compounds that come out of, usually it's going to be aged in oak barrels. So some of the compounds coming out of the wood, the organic compounds, are also going to affect the flavor. Okay, so let's look at how we can classify alcohols. So there's 3 ways that we can classify alcohols. So primary, secondary, or tertiary. And this is based on the carbons that are attached to the carbon the hydroxyl group is located on. So with primary alcohols, we see that the hydroxyl group is attached to a carbon that only has one other carbon attached. Everything else attached to it is a hydrogen. For a secondary alcohol, we see that the hydroxyl group is attached to a carbon that has 2 other carbons attached. So it's kind of more centrally located in a chain, for example. And then for tertiary, you probably could figure this out. We have the hydroxyl group attached to a carbon that has 3 other carbons attached to it. Okay. So what are some common alcohols? Because you do need to be familiar with some of these common compounds and their uses. So methanol, sometimes called wood alcohol because it was originally kind of identified as something that is produced when wood is destructively distillated. And so one thing is that it's extremely toxic. This is actually can be a problem when people try to create their own alcohol, and they have, if there's any kind of like contaminant in it or improper distillation process, then methanol can be produced, and it can cause death and blindness. So if you've ever heard, you might have heard of stories of like bootleggers back in the day and stuff, of people going blind from drinking alcohol that's not properly produced. So definitely a bit of a risk there. What is methanol used for? It's used in a lot of industrial processes. Like it could be used in antifreeze, it can be used in windshield deicer, windshield washer fluid, for example. All of those things contain methanol. So I have a little video in there about methanol poisoning too, if you're interested in seeing a little bit of information about that. Another common alcohol, probably the most common alcohol that most people think of, is ethanol, which is known as grain alcohol because it comes from distilling grains to form alcohol that's found in alcoholic beverages. Okay, and it's also used in the production of vinegar. There's some other information here about ethanol also being used in gasoline, and yeah, so it's not just used for like food production and consumption. What about naming alcohols? Similar rules again with naming alkanes, a few additions or modifications. So the prefix again gives the position of any side groups or branches off the main chain. The root indicates the number of carbons in the longest continuous chain, but you have to be careful here because your longest continuous chain has to contain the hydroxyl group. Okay, so make sure when you're counting out the parent chain that you include the carbon that has the hydroxyl group on it. For the suffix with an alcohol, we drop the regular ending and add OL to represent that it's an alcohol. So if you have an E, like say propane ends with an E, you drop that E and change it to propanol. Okay. The location of your hydroxyl group must be indicated. So just like with the alkenes, we would put in like pentan -2-ol, and the carbons are numbered from the end closest to the hydroxyl group. If you have more than one alcohol group, because that is a possibility for your alcohols, use di, tri, tetra, etc. to indicate the number of hydroxyl groups. So for example, pentane 2,3-diol. So in this case, if you have that, you don't drop the ending, the E, okay? So you're only going to drop the ending when you have, let's see, if you have just the OL is the rule, okay? But if you have that prefix like di, tri, then don't drop the E. In terms of naming cyclic alcohols have the same naming rules as other cyclic hydrocarbons, so you add that cyclo in front. If you have side branches present, start numbering from the carbon with the hydroxyl group. So if there's only one hydroxyl group, you don't need to indicate the number of the branch. So this one, for example, here, it's always going to be carbon 1, right? You always start with the hydroxyl group, so that's why you don't need to number it for a cyclic hydrocarbon. Okay, so we just have 2,4-dimethyl, still the numbering for the other groups, but not for the hydroxyl group. If you have 2 hydroxyl groups, 2 or more, then you do need to give the number of the locations. Okay, so in this one we have cyclohexane, and again you see that rule where because we have this di prefix, we haven't dropped the E here. So cyclohexane -1,3-diol. Naming aromatic alcohols, you don't need to know a lot about this. Basically, like you don't need to know how to name these. The only thing you have to know is what a phenol is. So phenols are just benzene rings that have a hydroxyl group attached. There could be other side groups, but you only need to know phenol. Okay, so basically you just need to recognize that if you see this substance, it's called phenol. And you should also be, of course, aware of the difference between phenol and cyclohexanol, okay? So just keeping in mind that this is an aromatic with those alternating double bonds and you have the hydroxyl group, it's always going to be called phenol, whereas if you don't have those multiple double bonds, you're going to be calling it the cyclo, and then you do need to know those naming rules that we just went over with that. Let's try a couple of questions here with alcohol boiling points. So the first question is, why is the propane, oh sorry, I think Actually, I deleted that in the new set of notes, so hopefully you guys don't have that in there. Why is propane a gas at room temperature, but propan-2-ol, also known as rubbing alcohol, is a liquid at room temperature? So here we have our structures, propane, right, just the 3 carbons with all hydrogens attached, saturated. And then for this one, we have basically the same structure, but one of the hydrogens in this central carbon has been replaced with this hydroxyl group. So with propane, the main thing is there's no polarity. The only intermolecular forces that would exist for this are London dispersion forces, right, which are quite weak. So therefore, it's not going to take a lot of energy to separate this propane molecule from other propane molecules because there's not a lot of intermolecular forces keeping them together. With the like the rubbing alcohol here, this hydrogen bonding is the strongest type of intermolecular force, and so we're going to see that this propan-2-ol molecule will want to stick fairly strongly with other ones because they're going to have that opposite opposite polarity that's going to link them together, the positives and the negatives. It's going to be quite magnetic between them, so it's going to take a lot more energy to separate multiple versions of this molecule from each other. So it has London dispersion and dipole-dipole forces and hydrogen. I don't know how I missed out on putting that in there. And hydrogen bonding. Therefore, it has a higher boiling point than its similar counterpart that doesn't have the hydroxyl group. And so it's a liquid at room temperature, right? Because at room temperature, it hasn't come to a boil yet, whereas for propane, it has. Okay, we did that already. One more question about alcohol boiling points. So we have glycerol, which is propane 1,2,3 triol. So remember what that means. We have 3 alcohol groups or hydroxyl groups located on each of the 3 carbons in propane. So here you can see the structure. We have the 3 carbon chain. Each carbon has a hydroxyl group off of it. Okay, so glycerol is more viscous than water. Viscous means like kind of like thickness. So it's like honey, for example, is more viscous than water because when you pour it, it's going to have that long, slow kind of like movement, right? Versus like water just runs right out. So glycerol is more viscous than water and can lower the freezing point of water. So basically that means that if water normally freezes at 0, it can make it so that water freezes at like, I don't know, -3 or something. I don't know what the actual numbers are, but it means that it's going to make it so that it doesn't freeze as easily. So if you add glycerol to biological samples, it helps to keep the tissues from freezing, thereby reducing damage. Because if you freeze biological tissues, you damage them, right? So from your knowledge of the molecular structure of glycerol, suggest reasons for these properties. Well, if we look at what glycerol is like, we can see that it has all of these hydroxyl groups, so multiple instances of hydrogen bonding, which means that it's going to have very strong intermolecular forces, right? So if we think about like its viscosity, for example, the molecules themselves are going to be sticking with each other very strongly because of these strong intermolecular forces. So that would be one explanation. The other thing is if we have this mix in between water, it's actually going to, because it's so polar and has the hydrogen bonding and everything like that, it's actually going to interfere with the interactions between water molecules. So if this is between 2 water molecules, those water molecules, if you lower the temperature, even though they're going to like want to move in closer, this will interrupt that bond because of its polarity. It'll keep the water molecules separate from each other. And because basically the water molecules will be strongly attracted to the opposite polarity on this molecule. So instead of bonding with each other, they'll kind of surround this glycerol molecule. And so because you're interfering with those interactions, the water molecules are going to stay separated for longer, and thus they're not going to freeze, right? Which basically means they're not going to join together to solidify as easily. Yeah, so that's basically an explanation. It's interfering with those interactions. Now, I don't actually have a lot of naming practice in here, or examples for alcohols. So, but you do have some practice problems, especially to think about the boiling points. And so what I would recommend is you pause the video now and try these questions on your own. The answers are in there, so if you get all of the questions and they all make sense to you, then you can just stop the video and don't watch anymore. If you're struggling a little bit, then you can come back and watch what I'm doing here, and I'll also go through some of the structure naming here too, so it can be a little bit of practice for that. So with butane 1-ol, what do we have? We have a root that has 4 carbons, and on one of those carbons we have an alcohol group. So I'm going to do this one, has an OH group to it, and the first carbon, so it has 1 bond and it's going to have 3 remaining bonds. 1 will be to the next carbon and 2 will be for hydrogen. So I'm going to do CH2 and then CH2, CH2. So that's 3 carbons and I need 1 more to make it 4 for butane. So that's going to be CH3. So butane 1-ol looks like that. And then for pentane, we're just going to have CH3, CH2, 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 1, 2, 3, 4, and 1 more CH3. Then we have 1-chlorobutane. So again, 4 carbons and a chlorine group off of the first one. So let's go Cl-carbon, and again, this one will have room for 2 hydrogens, CH2, CH2, and a CH3. So there's our 3 structures. And we want to predict the order of increasing boiling points for the following compounds. So the highest boiling point here is going to be the alcohol because it has both dipole-dipole bonding, because there's like a little bit of polarity here. Even though it is a longer chain, there will still be a slight polarity here at the end. And it also has hydrogen bonding. So it has 2 types of intermolecular forces. Well, actually, sorry, it has all 3 because everything has London dispersion. So this one will be highest boiling point because of those 3 types of intermolecular forces. Now with chlorobutane, you're going to see that there is like a little bit of polarity again from that chlorine, so that means it has a little bit of dipole-dipole intermolecular forces as well as London dispersion. So this one will be our next highest, so second highest. And then pentane is going to be our lowest. So even though we have 1 more carbon in this, there's no polarity at all to it. So it only has London dispersion, which automatically makes it the weakest. So that is our ranking of the boiling points as well as reasons. Make sure in a test question you remember to give the reasons, the types of bonding. I haven't written them out here because I don't want to waste your guys' time, but verbally I've kind of given those to you. So make sure that in a written test question you would actually write that all out. Okay. Practice number 2, 2 properties of alcohols that are due to hydrogen bonding would be, so remember hydrogen bonding is that stronger polarity kind of and stronger force that keeps the molecules together. So when we have stronger forces, that always raises the boiling point. So we see that there's higher boiling points in alcohol. And the other thing we see is that when you have that type of polarity, substances are going to be more highly soluble in water, which is also polar. So we're going to see high solubility and high boiling points. So D would be the correct answer for that one. Practice number 3, the molecule hexanol contains which functional group? So as soon as we see that OL, we know it's an alcohol, and all alcohols have hydroxyl groups, right, which is that OH group. Now we have kind of more of a diploma type question, so they just want us to find the organic compound numbered above. That is an alkene. So just looking at the endings, we can see here's an alkene, so that would be number 1. An alcohol always ends with OL, so that would be 6. If it contains a triple bond, that's an alkyne, so that ends in YNE, so that would be 4. and then a cyclic and saturated. So if we look through our different ones, we have cyclo here and cyclo here. So you need to choose between both of them. This one has like a functional group off of it, an alkyl group. Remember, for something to be saturated, it has to only have the carbons have to have as many hydrogens as possible. So that would be cyclopropane. There's no hydrogens that have been replaced by a side group. So cyclopropane would be the correct answer there. Last of all, we have the molecular formula for 2,5-dimethylcyclohexane 1-ol is, so we need to figure out how many carbons, hydrogens, and oxygens would be in this structure. So in order to do that, we have to draw it out. So I would start out by thinking about the root cyclohexane, right? So I'm going to have a cyclic structure with 6 carbons. So that's always going to be that kind of a shape. Then it has, on carbon 1, of course, it has the alcohol group. And then on carbon 2, it has 2 and 5, it has a methyl group. So that's going to be CH3, carbon 2, carbon 3, carbon 4, carbon 5, CH3. Okay. So now we just need to think about how many carbons do we have, how many hydrogens, how many oxygens. We have 6 carbons in the ring plus the extra 2 on the methyl group. So we have C8. H is probably going to be our trickiest one here because we're going to have carbons 3, 6, and then for each one that doesn't have a side group, there's going to be 2 hydrogens. So we have 6, 8, 10, 12. And then for the ones that have a side group, we're going to have 13, 14, 15, plus we have the hydrogen on here, so that's going to be 16. Okay. Then the only oxygen we have is on the hydroxyl group, so it's going to be O. So C8H16, O is going to be the correct answer for that one. Okay, so that's how you would sketch out something like that. A little bit of information there about a comet, pretty crazy. It's releasing as much alcohol as would be in 500 bottles of wine every second, and it's the first time ethanol has been seen being released from a comet, so that's kind of cool. Okay, so you guys have some practice problems. Again, please make sure that you are checking the solutions to make sure that you're doing this correct, especially because we didn't do a lot of examples of naming with alcohols. And I will see you in the next lesson where we're looking at carboxylic acids and esters.